Okay, let me introduce Professor Alex Wilkie. Professor Alex Wilkie is the professor at Oxford University, and prior to his current position at Oxford University, affiliation with Oxford University, he was at the University of Manchester, and there is where I met Professor Wilkie, where I took a model theory course from him. Professor Alex Wilkie is also the FRS professor. Is that right, Professor Wilkie?
I'm emeritus now. In fact, I'm what's called an emeritus research fellow. So I used to be the field and professor of pure mathematics at the University of Manchester.
Okay, I see. So Professor Alex Wilkie is a very accomplished model theorist, and it is our pleasure to welcome him to speak to us about some remarks on the model theory of analytic functions. Professor Wilkie, it's all yours.
Thank you very much. Thank you very much, Su Yao. And it's a great pleasure and privilege to be the first speaker at the inaugural conference, the very first conference of the Logic Association of Malaysia. And to have taught its president. So I was an undergrad. Are you hearing me, everyone? Yeah. Can I just check?
Yes. Yes, I can hear you.
Yeah. Okay. Good. Because this is the first time I've done one of these Zoom lectures, and of course it's a bizarre experience when you can't see the audience. But anyway, so I was an undergraduate at University College London, and you could not do a course in mathematical logic there. In fact, there were very few universities in the 60s in Britain where you could, so a bit like your situation maybe now. In fact, I did manage to do a course in logic. I had to walk down the Euston Road in London to Bedford College London, where I did the course, and eventually I went to Bedford College to do my PhD under Wilfred Hodges. If you've read any model theory at all, you might know his book. Now, I soon became interested in model theory. I was particularly interested in how it could apply to actual mathematical problems. I started off looking at number theory and models of piano arithmetic, which was what my thesis was in. But eventually I changed. As an undergraduate, I suppose you have preferences to the particular subject you like, possibly either algebra or if you're a pure mathematician, or analysis. I was always more fond of analysis than I was of algebra. I think most model theorists are possibly the other way around, but anyway, so I got very interested in Tarski's early papers about the ordered field of real numbers, and in particular the problem he posed about analytic functions, and in particular the exponential function. So let's just start with Tarski's early work. So that this is about the structure which I always call R bar, which is has domain the set of real numbers with the usual ordering and the usual algebraic operations of addition and multiplication. I'll let L be the language, the first order logical language of this structure, and T to be the theory of this structure, the set of all sentences in first order logic that are true in R bar. And Tarski regarded this really as the structure for elementary algebra and geometry. That's what his paper was called. So in the sense of geometry as regarded as the study of Cartesian coordinates, usually in the plane when one's at school, but of course it can be in any number of dimensions. And what it's a theorem that goes by the name of the Tarski-Seidenberg theorem, says the following: T admits effective quantifier elimination. So see a bit. This QE here is stands for quantifier elimination, and this means that if you give me any formula, phi of x bar of the language L, x bar is a tuple, an n tuple of variables, free variables in the formula, then you can find effectively, and in fact, the proof actually gives the algorithm, a quantifier free formula. QF means a formula without any quantifiers at all, which is equivalent to the formula you were first given. So in other words, T proves that for all x bar, phi x bar is equivalent to psi x bar. So that was the theorem. And there are several consequences of this. So we can apply this for n equals 0 here. So when there are no variables at all, so when phi is just a sentence, and that tells us that T is decidable. In other words, given any sentence phi, we can decide whether or not it's true in the real numbers with the algebraic structure. And this is because we effectively find the quantifier free sentence that's equivalent to it. And quantifier free sentences are easy to decide. They are just algebraic manipulations of the numbers 0 and 1 with addition and multiplication applied to them and the ordering. So we can easily decide quantifier free sentences of this language. That is obvious here, but is not true for almost any other structure we'll be considering. But anyway, another thing that the proof of the Tarski-Seidenberg theorem gives us is that you can axiomatize T in a very nice way by a theory that's called RCF, which is the axioms for a real closed ordered field. These are simply the axioms for fields, together with the statement that every positive element has a square root and every polynomial of odd degree has a root. Okay, those are obviously true statements. Oh, I should have said, if you look at the terms of this language, they're essentially just polynomials with integer coefficients. Okay, if you just combine plus and times and 0 and 1 and variables, you just get polynomials. So the axioms for real closed fields are just those axioms. And it turns out the whole proof of Tarski can be done in this theory. So we get that the axioms for real closed fields axiomatize T and therefore axiomatize what Tarski calls elementary algebra and geometry. So that's the situation for sentences. Now we're going to be very interested a bit later on in formulas and the sets that the formulas define. So let us look at the formula with just a single free variable, phi of x1. So let us now, without loss of generality, assume that it has no quantifiers. So it's really just a Boolean combination of formulas involving polynomials, polynomial equalities and inequalities. So the set defined by this formula here is just those real numbers that satisfy the formula. That's what you mean by the set defined by the formula. So what can it be? It's just inequalities and equalities between polynomials with integer coefficients in one variable. Well, if you think about it, a polynomial only has finitely many roots, and it's really those roots that will determine, so the position of A relative to those roots that will determine whether or not phi of A is true. And so you observe easily that this set defined by phi is just a finite union of intervals with algebraic endpoints. An algebraic real number is just one that satisfies a polynomial equation with integer coefficients. Interval here, I mean a generalized interval. So it can be closed, open, half closed, or even a point, or it could be semi-infinite as well. So generalized intervals. And Tarski explicitly in another paper actually mentions this, that the only sets that are definable, subsets of R that are definable in the language, our language here, are just finite unions of intervals. In other words, they can just be defined using the ordering and parameters for the endpoints. And in fact, and this will be important later when I discuss the subject called own minimality, the same is true if you allow what we call parameters. So if you take a formula in n free variables and you substitute a2 up to an, just arbitrary real numbers, for the last n-1 variables, then you still get a formula in x1, and the same is true. Here, the endpoints of the intervals are still, you still only get finitely many, union of finitely many intervals, but the endpoints this time will just be algebraic over the field generated by a2 up to an. I don't know how many people have done sufficient algebra to know this notation, but it doesn't matter too much. But the point is that the number of intervals that you get, and this is absolutely crucial later on, the number of intervals depends only on the actual formula with the variables there, and it doesn't depend on the choice of the parameters. And that's because the parameters in the quantifier free form of phi will only appear as coefficients of powers of x1 in the various polynomials that occur in the expression. And of course, the number of roots of a polynomial only depends on the degree and not on the coefficients, or an upper bound for the number of roots can be found depending only on the degree, but it is the degree, and not on the coefficients. So if we go back, so the finite union of intervals here does not depend on the parameters a2 up to an, the number of those intervals. It only depends on the general form of the formula phi. Okay, are people still hearing me, and do people want any clarification so far? Everything okay? You can still hear me. Sorry, I need reassuring.
I can still hear you.
Yes.
Yeah. Okay. Yeah. Okay. Good. Okay. So that was the situation. That was the situation for just the algebraic structure on the reals. So now let's go to a question that Tarski poses in his paper, actually, which is about the following variation. So here we have the structure R bar, that's just the algebraic structure and ordering structure on R, together with the full exponential function. This is just the function x maps to e to the x, which seems to be the next natural function to consider, especially if you're an analyst. It's the next most popular function, one might say. And so I'll let Lx just be the first order language of this. So this is just the same as the language of R bar, but with an extra unary function symbol for exponentiation, and let 2x be the theory of this. Actually, before I go on, there's an observation of Van den Dries as follows. So the theory of R bar is really just the theory of coordinate geometry, theorems about lines, circles, and so on. And so Tarski proved any such question is decidable. Van den Dries says, well, the theory of Rx is really the theory of hyperbolic geometry, because the metric there involves, well, exponentiation and logarithms. So this is to task his original theorem, studying this structure, as hyperbolic geometry is to ordinary coordinate Euclidean geometry. Anyway, so what about the corresponding statements for this structure? Well, let's see how I'm doing for time, that's fine. Well, first of all, quantifier elimination is actually false. That goes back 100 years, not phrased in that way, but Osgood, an American analyst in the 1920s, constructed, in fact, a quantifier-free formula in this language, such that when you project it, the result, which is really just existential quantification, the resulting set no longer can be expressed by a quantifier-free formula. So that's false. So what about decidability? Now, model theorists these days tend not to emphasize decidability questions, but I'm going to for a little while, and then we'll get on to what we call definability questions. So, okay, so for decidability, well, this opens a real can of worms, as we say. So let's just look at some quantifier-free sentences here. I mentioned that these can be problematic. You see, if Tx were decidable, so would be the set, this set here, which I've called lambda, the set of positive integers p and q, or non-negative integers p and q, such that e to the p equals q. Right, so e to the p equals q is just a quantifier-free sentence of this language for each fixed p and q. So if we could decide Tx, we could certainly decide whether this is true. But as far as I know, even this is unknown. So given positive integers p and q, can you decide if e to the p equals q? I really think that's unknown. You might think, well, I can effectively approximate e to the p by rational numbers in many different ways. But the problem with that is you get closer and closer to this value with rational numbers and then ask if that rational number is equal to q. Well, it might get closer and closer to q, and you never really know if you're going to hit q. So really, that's a proof that this set is what we call co-RE. It's the complement of a recursively enumerable set, because eventually, if this is not true, if this does not equal q, you'll eventually find out that by approximating this. But it's not clear whether this is a recursively enumerable set. So in other words, we do not know an algorithm to decide this. Of course, we don't even know if e to the p is rational for any p, but this is a apparently easier question. Can you decide whether it's equal to a given integer? And so the decidability of Tx already involves some incredibly difficult questions of our transcendental number theory. However, we do have some positive results. Oh, by the way, let's go back. Why didn't I just say e to the p equals q? Well, that is known. That can only happen if p is 0 and q is 1, because e is a transcendental number. So e to the p can never equal q, an integer, unless p is 0. So the set is obviously recursive, but that's about the limit. Things like one level of exponentiation is about the limit. Anyway, we do have some positive results. So this I proved about 30 years ago after working on it for 4 or 5 years. together with other people, I should say, Van den Dries and McIntyre in particular, TX is what we call model complete. So not every formula is equivalent to one with no quantifiers, but every formula of LX is equivalent, modulo this theory, to an existential formula. So that's a logical formula where you have some existential quantifiers followed by a quantifier-free formula. But to this day, we still don't know. The proof's not effective, my proof, but there might be another proof that is effective, but it's still not known if this model completeness is effective or not. But to decide this, I mean, this is something worth working on, because I don't think this should involve any transcendental number theory. You won't have to know any complicated stuff in order to do this. It's just a question of getting a better proof than mine. And I say that because if, this is the theorem of myself and McIntyre, instead of considering the full exponential function, you only consider its values restricted to the, say, the closed interval 0, 1, and make it 0 elsewhere or something, that is effectively model complete. You given any formula of this language, the language of this structure, well, which is the same language, but you can find a quantifier, existential formula that's equivalent to it, and you can find it effectively. Although I'm certainly not saying efficiently. Oh, perhaps I should have said in my discussion of the Tarski theorem, it's a very big ongoing subject to make the quantifier elimination there more efficient. It's a big subject called computational real algebraic geometry. Perhaps I should say that Tarski's algorithm was not even what we call elementary. It involved, it's not the efficiency was not even bounded by an iterative exponentials, but it is now. There's better proofs. Anyway, here I don't know anything about the efficiency of the algorithm here, but so you see, this suggested that TNT is transcendental number theory. Another favorite subject of mine as an undergraduate, by the way. This suggests that TNT issues are no obstruction to effective model completeness. They're obstructions to decidability of the whole theory, but one, you see, all transcendental number theory issues to do with, oh, wait a minute. Sorry. All transcendental number theory issues in TX occur in T restricted X. They have exactly the same what we call definable numbers here. So the equivalent of the algebraic numbers for R bar, there's an equivalent to that for this theory, and they're the same. So the transcendental number issues are no obstruction to effective model completeness. So this means, as before, that if you're given any formula of this language, you can effectively find an existential formula equivalent to it. Okay, now we do have a, McIntyre and I did prove an effectivity result for the whole theory, but in the sense that we isolated the exact facts about transcendental number theory that are needed. And then really for logic, that for model theorists, that's the end of the story. I mean, we're not number theorists. So what I've really shown so far is if there's ineffectivity, it lies in the existential theory of Rx. So we've done the logic right down to the existential theory. That's the issue. So those are the sentences that can be written as existential quantifiers, followed by a quantifier-free formula. So all these transcendental number theory issues, all problems disappear if we assume a positive answer to a very famous conjecture of transcendental number theory. And so this is the following. So it's a very famous conjecture called Shanel's conjecture. I'll call this SCR because we'll later look at Shanel's conjecture for the complex numbers. So the conjecture says the following. For any n and for any sequence n of real numbers, which are linearly independent over the rationals. So that just means if you take any rational linear combination of alpha 1 up to alpha n, if that's 0, then all the rationals must have been 0. So there's no non-trivial linear combination of these which are 0. So if alpha 1 up to alpha n have that property, for example, alpha 1 might be 1 and alpha 2 might be root 2, the square root of 2. They're linearly independent. But, okay, but if you take any n numbers for any n which are linearly independent over the rational. Hello, can you still hear me?
Yes,
You
yes.
still, just the battery's running low. I don't know why, but anyway. Then this field, so this is the field generated by alpha 1 up to alpha n and e to the alpha 1 up to e to the alpha n, has transcendence degree at least n over q. So what this is really saying is that the only algebraic relations between real numbers and their exponentials come from the laws of exponentiation, just come from the law e to the x plus y equals e to the x times e to the y. Now, this is known for n equals 1. It's a famous theorem of Lindemann from 1882, which is essentially the theorem that if alpha is an algebraic number, then which is not 0, then e to the alpha is a transcendental number. So it's known for n equal 1, but it's not known in general for any other n. Let me give you an example to show you how it settles the question of that set lambda I mentioned before. So suppose we take alpha 1 to be 1 and alpha 2 to be e to the p, where p is a positive integer. Then they are certainly linearly independent over q by the theorem I've just stated, Lindemann's theorem. Okay, because e is, in particular, e is not an algebraic number, so certainly 1 and e to the p are linearly independent. So if we assume Shanel's conjecture for the reals, this implies that the transcendence degree over q of the numbers alpha 1, alpha 2, that's 1 and e to the p, and their exponentials, which is e to the 1 and e to the p, that transcendence degree is greater than or equal to 2. That's what the conjecture predicts. But that immediately implies that e to the p cannot be a natural number, because otherwise we just have 1 e to the p, e, and a natural number, and that's another way of writing that field is just q of e. So these elements would all lie in this field here, and that has transcendence degree just 1. Okay, because it's just q adjoin one more element. Whoops. Okay. So that's a contradiction to Shanel's conjecture. So that set lambda we had before, the recursive set, is a decidable set. Okay. Now, it turns out that if we assume Shanel's conjecture, then all our problems disappear. Oops, gone the wrong way, sorry. Perhaps I'll say first that why there's a connection between Shanel's conjecture and sort of logic or universal algebra anyway. An extension of this argument actually shows, and McIntyre showed how to do this, that the closed terms of LX, that's just the terms with no free variables, form a free algebra. So hence the relevance of this. So any expression involving integers plus times and exponentiation with no variables, you just build up an expression like that. Unless it's not obviously zero, then it isn't zero. That's really what one thing Shannon's conjecture is telling you. So you build up e to the e plus e7 plus 7 times e squared and things like that. Unless you can break down that expression using the laws of exponentiation and laws of algebra, then it cannot itself be zero as a number. Anyway, McIntyre and I showed that Shannon's conjecture for the real numbers does imply that Tx is decidable, essentially due to this freeness here. And hence, obviously, it's effectively model complete, but that's a weaker statement now. So we thought that was the end of the story, really. So we're not going to be able to prove or disprove Shannon's conjecture. Nevertheless, I was never really happy with this because there's no great evidence that Shannon's conjecture is true, in my opinion. I wanted to try and formulate a conjecture. Okay, let's go back again, which was actually equivalent to Tx being decidable. I mean, it's all very well stating this grand conjecture, but I mean, Shannon's conjecture is probably not as assumed in the number theoretic community as is the Riemann zeta hypothesis, for example, or anything like that. You often see theorems based on that, but people tend not to assume Shannon's conjecture and see what follows. I've got a story about this that goes back to my very early days in Oxford, when there was a very famous logician, Kreisel. I don't know how many people there are in the audience here remember or know of the work of Kreisel. He was very, very influential mathematical logician in the 50s, 60s, 70s, 80s, and a very marvelous mathematical logician, had a very wide range of expertise. And McIntyre and I were in the common room in the Mathematical Institute of has my screen gone blank, by the way?
It's still there. We can see.
It's still there. Oh, yeah.
No,
okay.
it just went black. It just disappeared.
Oh, something. Oh, I've collapsed here. I've only got, oh dear. I need to plug this in. I didn't check that beforehand. What do I do here?
You might need to wait for it to start again.
Yeah, wait a minute. Can you bear with me? I'll have to just go and plug the iPad in. I'm very sorry about this. It'll just take me 2 minutes.
Sure.
Okay. Okay. Am I back again?
We haven't seen your screen.
Okay. I'll have to. So sharing content again. Start broadcast.
Yes. Okay, we're seeing your screen.
Okay. Screen. Yeah. Zoom.
Yeah.
Yeah.
So you have to touch your screen outside the the stop broadcast.
Stop broadcast.
No, you don't want to touch that. You want to touch outside that gray box.
Oh, I'm sorry. Yeah, we did that before. Okay. Right, now I want to get back to bamboo paper. There we are. Okay.
Okay. Good.
We're all right now, right?
Yes.
Okay. I'm still sort of on time, so. Right. Okay. So I was telling you the story of about why. Well, certainly I'm skeptical about assuming Shannon's conjecture, and this was brought home to me, and I suppose it was a coffee in the morning in the Mathematical Institute in Oxford a long time ago, where there was McIntyre, myself, and Kreisel, that I'm sure some of you know of, or at least know of, was there. And also Brian Birch, a very famous number theorist, famous for something called the Birch-Swinnerton-Dyer conjecture in number theory. It's actually one of the Clay millennium problems, that, but he was there. And we mentioned this result, that we could prove decidability of the theory of the real exponential field if Shannon's conjecture was true. And then Birch said, oh gosh, if you assume Shannon's conjecture, I can prove anything. And then Kreisel said, what, even the negation of Shannon's conjecture? Which was rather typical of him. But anyway, I didn't much like assuming Shannon's conjecture. So we looked for something that was actually equivalent to the decidability. And this is it. Unfortunately, this is not just purely a number theoretic statement. It does involve decidability, but it does turn out to be exactly equivalent to, and it's the decidability of TX, but it's really slightly more mathematical. It doesn't mention logic, at least. Okay, so this is something we call the first root conjecture, FRC, and the conjecture says the following: given n and a function fx1 up to xn, which is a polynomial in the variables x1 up to xn and their exponentials. Okay, so given a function like that, and that's a kind of decidable data, right? You can effectively enumerate this set here. One can effectively find a positive integer eta, which just depends on n and f, with the following property. If f does have a 0 in R to the n, n-dimensional Euclidean space, then it actually has one whose coordinates are bounded in modulus by this number eta. And the crucial thing about this is that eta has to produce an output for every input. So even if f does not have a 0, eta must provide you with a number, and it must be effective. But if it does have a 0, it's got to have one less than eta. So in other words, can you effectively find a number such that if a function like this has no zeros bigger than that number, then it has no zeros at all? Sorry, if it has no zeros less than that number, then it has no zeros at all. Anyway, so that's the sorry, I keep doing the wrong one. So that was the thing we found that's equivalent to the decidability of TX. So it's a kind of sort of number theoretic statement that's actually equivalent to the decidability of TX. That conjecture is equivalent. And that's where we really leave the story about decidability. And I think for none of the other structures do we really consider the decidability question. We go on to the issues of definability in general, and particularly of that statement 4 about every definable subset of R being a finite union of intervals. So this brings me on to this very popular topic now of O minimality. So here we take an arbitrary expansion, which I call R tilde of R bar. So we take a structure R bar, which has some extra, well, I just say functions here, but they could be relations, but usually they're functions that are functions of some interest analytically. And we let L be the language. And then, so I want to now quote to you from Van den Dries's book on the subject of O minimality, and it is the only textbook to date on O minimality. It's highly recommended. And so the point is here that you would only be looking at expansions like this if you had some interest in these functions. So let's suppose that we know something analytically, mathematically, about the quantifier free definable sets. And as model theorists, we start to apply the logical operations of the Boolean operations and the quantifiers, and we get more and more sets that way. And in his book, Claim Topology and O minimal structures, Van den Dries notes that 2 things might happen when you start applying logical operations to well-defined sets. And the first thing, which is slightly undesirable, is that, no, the first thing is the desirable thing. After only a few such operations, say, after taking projections of finite unions of the sets we start out with, a stabilization occurs, and performing further operations does not produce any new sets. But the other thing that could happen is ever more complicated sets arise, Cantor-like sets, Borel sets of arbitrary high complexity, and so on. And he says it's phenomenon 1 that is of particular interest to us. Here we remain in the realm of geometry and topology envisaged by Poincaré. Yeah, someone's written up there. In the sense of Poincaré, and we may view the study of the corresponding category of nice spaces and maps between them as an unfolding of the rich algebraic analytical topological structure of the continuum. When phenomenon 2, on the other hand, is pursued, then the ties to geometry tend to become very loose. We enter here Cantor's paradise. Only set theoretic features ultimately survive in this bleak landscape. Already on the Borel level, the real line and the real plane, or Cantor space for that matter, become indistinguishable. So in other words, model theoretically, you want the logical operations not to increase the complexity of the quantifier free definable sets by too much. And Van den Dries had the incredible idea, which turned out to be incredible, but it had certain motivations, to make the following definition. He said, our expansion is called O minimal if every L tilde definable with parameters, and that's important, subset of R, is a finite union of intervals, So in other words, this is where the word minimal comes from. They have to be, they're just definable with the ordering. Okay, that's what minimal means. And sorry, that's but unfortunately, Van den Dries couldn't completely develop the theory because he could not prove that that extra property I mentioned earlier holds. In other words, that the number of intervals is independent of the parameters. There should be an upper bound on the intervals that are independent of the parameters on the number of intervals. And he couldn't prove that from that definition. And so that was proved, however, later by Pillay and Steinhorn in a couple of papers, one of them with Julia Knight, that uniformity in parameters, in the sense I just stated, actually follows from the definition. So then his whole book develops the theory of O-minimal structures. Well, that would not be very interesting if the real field was the only example, but there are plenty of examples now. So first of all, we'd obviously have R bar by Tarski, as I mentioned, that's O-minimal. Rx is also O-minimal. The proof of that follows from an old theorem of, well, it was not that old, but it existed before we proved the model completeness, of Hovansky, sort of a Russian geometer. He showed in this quite famous book called Phonomials, he showed that if you take any quantifier free Lx definable subset of R to the n, so this is in n variables, it's a finite union of connected, topologically connected sets. So it follows that the same is true of a projection of such sets, because projections are continuous in the usual topology, and the continuous image of a connected set is connected. So in particular, if you project down into one dimension, you just get a finite union of connected sets, which is the same as saying it's a finite union of intervals. And since we know every set by model completeness is the projection, just the existential quantification of a quantifier free set, we get the O-minimality of Tx. And Gabrielov proved, and this is hence the title of my talk really, that this very famous structure Rn, so this consists of the real field where you add all functions restricted to this open set for all n, where f is analytic, and that means, so An consists of those f which are given by power series which converge on something bigger than the interval 0, 1. So you take a large interval containing the open interval 0, 1, and if f can be expressed as the sum of a convergent power series on that set, and then you restrict it to 0, 1, you just add all those functions. So those are the so-called analytic functions, restricted analytic functions. Then that is O-minimal. And the extension here is necessary because you have to avoid functions like sine 1 over x, which is an analytic function on 0, 1, but that has infinitely many zeros. So you couldn't possibly have an O-minimal structure with that as a definable function, because its set of zeros is not a finite union of intervals. So, but this does not have an extension to 0. So, so you have to avoid that. So the convergence has to be on a bigger set there. Actually, this structure does have quantifier elimination if you add a function symbol for 1 over x and say that's 0 if x is 0. Then you do get quantifier elimination. Gabrielov just proved model completeness. And then finally, well, not quite finally, but Van den Dries and Miller then proved you could even add exponentiation to that Rn. And this is the structure when there are a huge number of applications now of the O-minimality of this structure. This is the one that's almost the only structure that's used now by number theorists and geometers, the O minimality of the restricted analytic functions together with the full exponentiation functions. And a huge number of examples now. People construct them all the time, and I'm hoping to see some new ones tomorrow in Athipat's talk tomorrow. So he mentions tame solutions of certain functional equations, and by tame I'm assuming he means O minimal. So with so many O minimal structures, you might ask, is there actually a maximum O minimal expansion of the real field? There's obviously maximal ones by Zorn's lemma, but it turns out there is no maximum O minimal expansion. One can construct two incompatible O minimal structures, but that's a slightly minor result. So why is this O minimality definition so good? Why do people now use O minimal structures so much? Well, it's basically because of the properties that Van den Dries proves in his book. He sets out a lot of the analytic and geometrical and algebraic properties of O minimally defined sets and functions. So let's fix an O minimal structure R tilde, and let's take a definable set, any definable set in Rn, R to the n. Now, even though the definition of O minimality says nothing about higher dimensional sets, in fact, one can prove that they have a property like being a finite union of intervals. They can be partitioned into things called cells. I won't go into the definition of what a cell is, but it's like an interval in many dimensions. In particular, it's a connected set. And further, even if you're given any definable function on your original set A, then you can always choose the CI, so the restriction of f to each CI is a continuous function. So definable functions are almost continuous. You can partition their domain into finitely many connected sets such that the restriction of the function on each of the sets is continuous. So you don't get any really wild behavior in definable functions. And that was Van den Dries's aim in avoiding arbitrary Borel sets and so on. Another property is that if you have any definable function of one variable, then it's piecewise differentiable. So you can partition R into finitely many intervals such that on each interval f is differentiable and even m times differentiable. Unfortunately, the number of intervals here does increase with m, and it's been shown in some O minimal structures that's the case. But in the useful ones, R tilde, if R tilde is Rn x, then actually any such f is piecewise analytic. So C infinity in particular, infinitely differentiable. So, so there are some properties of a few facts about O minimal structures. Oh, there's one last theorem I really must mention, which is I still fully don't understand why this is the case, but it's a restriction on what can be O minimal. If you're given any O minimal structure R tilde, so this is Chris Miller's dichotomy theorem, either the exponential function is already definable by a formula, in other words, its graph is definable by a formula of the language, or if not, every definable function has polynomial growth, and it's bounded in growth by a power of x, mod fx. So there's nothing really that you can have between polynomials and exponentiation. Of course, you can have definable functions between the two, like x to the log x and things like that. But if you do, you also have exponentiation. You can't avoid it. So that's still not fully understood theorem, really, why that should be the case. Well, okay, I think I'm going to finish there talking about, I've got 5 minutes maybe. I must say something about the complex case. So what here, it's very quick because we know very little. So C algebra is let that be just the complex field of complex numbers, and L its language. And one of the very early results of model theory is that this behaves even nicer than the real field. This is what's called categorical theory. So C-alg is the unique model in cardinality 2 to the L of 0 of the theory of algebraically closed fields of characteristic 0. Okay, I think I'm going to have to rush through this, but these are just to the effect. This has quantifier elimination. This is very well understood. This is the basis of the algebraic geometry, this structure, and it's very well understood. But what about if we add exponentiation? This was also, I think, a question of Tarski and other people. But the problem here is that there's a very simple formula here, which defines the integers. So the ring of integers is defined in this structure, which tends to make it look like the rather unsavory side of Van den Dries's dichotomy. And once you have the integers, you have all what we call Gödel phenomena, no decidability at all, and rather wild behavior, we would have thought, at least from a geometrical point of view. But if I can just say another personal note, so all model theorists thought that this is unstudyable in model theoretic terms because of this fact that the integers become definable. But this changed. I can give you the exact date. I think for me it was July the 8th, 1992, and this was the day that I happened to bump into Boris Zilber. I think it was on the Rue Saint-Jacques in Paris during the very first European Congress of Mathematics. So he posed the idea that the model theoretic study of CX might be possible, even though the ring of integers were definable. Of course, recall that in no minimal structures, the whole point of the definition is that you don't have things like the ring of integers definable. He said that, first of all, we must show that the set of real numbers is not definable. See, the trouble is, if you can also define the set of real numbers and you also have the set of integers, then you can define every Borel set. And even more than that, you can define what's called the analytic hierarchy in set theory. And that is hopeless model theoretically. There's no way back if you can define the real numbers. So first question, he posed as a conjecture, I think, that R is not an LCX definable subset of C. Now, this is very odd because the rationals are a definable subset. Q is definable because the integers are. It's easy to define Q from there. And you think, well, just take the closure. But of course, topological notions might not be interpretable in here. And that's what you've got to show. And this is still unknown, whether the reals can be defined using the ring operations in the complex numbers together with exponentiation. And then he went on, he said, well, that in itself would not be a great result. How about his conjecture 2? And I must say it's something I've been working on for, well, nearly 30 years now. Try and show that every definable subset of the complex numbers is either countable or co-countable. So we've got to admit countably infinite sets. We know that. But maybe if every set is either countable or co-countable, subsets of C, this is what's meant by quasi-minimality, then maybe we have a chance of developing the model theory. And so these are still unknown. Zilber himself went on to prove a spectacular theorem. He managed to write down some axioms such that the complex numbers with exponentiation is the unique model of these axioms in cardinality 2 to the L of 0. So, and the model, sorry, let me say again, he wrote down some axioms which has a unique model in cardinality 2 to the L of 0, and that model is quasi-minimal. So all you have to do is show that the complex numbers with exponentiation satisfies Zilber's axioms. I've written them down very quickly here. Unfortunately, Zilber's axioms include Schanuel's conjecture. So he has found a model of Schanuel's conjecture in which Schanuel's conjecture is true, and it has a unique model in cardinality 2 to the L of 0. But how do we know the complex numbers is that model? Well, we have to prove at least that Schanuel's conjecture is true, unfortunately. So although Zilber's axioms, which are not actually first order, I should say that, they're infinitary axioms, but he does have axioms where in each cardinality, it has a unique model, but we just don't know if that model in cardinality 2 to the L of 0 is the complex numbers. But I think my time's up. So it's been a great honor to give this first lecture in the first conference of the Malaysian Association of Logic. And thank you very much.
Thank you very much, Professor Alex Wilkie. It was a pleasure to listen to your talk. Maybe we have time for one question. Does anyone? Sugao, you have a question? Go ahead.
So I was clapping.
Oh, okay.
Thank you. Thank you very much.
So Professor Young is also clapping as well, or do you have a question?
Maybe a naive question. So in Zilber's axioms, other than Schanuel conjecture, other part of the axioms are not open, or it is known that the complex number satisfies.
Okay, good question. Okay, let me tell you quickly what they are. So here we take a structure with, in the language of exponentiation, with what we think is exponentiation E. And so phi is the collection of axioms which say the following. First of all, the algebraic part has to be an algebraically closed field of characteristic 0. E satisfies the usual laws for exponentiation. In other words, it's a homomorphism from the additive structure to the multiplicative structure in the usual way. Now, here's the non-first order axiom. You have to say that the kernel of this homomorphism, the set of points that take the value 1, is exactly the integers, or the integers times omega. Well, omega's like 2 pi I here. So there's a transcendental number omega such that the kernel is exactly Z. Z must not be non-standard, in other words. So that's a non-first order axiom. They're all right. They're all, of course, true. Here's Schanuel's conjecture. This 6 doesn't pose a problem. I haven't written it down. But here's what we call a dual Schanuel conjecture. It's like the algebraic closeness axioms. You have to show that every system of polynomial exponential equations actually does have a solution, unless that solution would contradict Schanuel's conjecture. So you have to phrase that, and it's quite complicated to phrase that properly. But even that is not known. You know, you have to, and not only that, it has to be a generic solution. So for instance, an example would be e to the z equals z. Now, it's not obvious immediately how to construct a z, a complex z that satisfies that, but there are plenty of them. But all equations like that have to have solutions. And that's not known either. Actually, it is now known that this is the only thing you need to prove quasi-minimality. You don't actually have to have Chandler's conjecture, but even this seems very difficult. This is the algebraic closure. It's the equivalent of algebraic closure. Is that okay?
Yeah, okay, thank you. Thank you very much.
So there's much more than Chandler's conjecture you need to prove to show that Silber's axioms are satisfied in a complex field.
Okay. Let us thank Professor Wilkie one more time, and then thank you, Professor Wilkie.
You're very welcome. You're very welcome. Great honor.
So.